My name is Kalena, and I'm the team leader for Team 7 Msc Wall. And I'm here with fellow team members Kyle, Jim, and Ashley. And our project is the Student GeoChallenge GeoWall 2012. Our advisors are Professor Pervizpour and Dr. Calabria of Geosystems Incorporated. And our senior project coordinator is Professor Marcus. Now for a little bit about what exactly our project is. We were to design, build, and test a mechanically stabilized earth wall to withhold 3 different loading cases, and it was part of a national competition. And before I get into each of the 3 loading cases, I figured I'd take a moment to explain what exactly is in the photo shown on the screen. Ooh. As you can see, the white poster board represents the Msc Wall facing, and the brown squares on the paper are the attachments to the reinforcement strips, and these strips are what exactly holds up the weight of the wall. And for the first loading case is self-weight. So in this particular step, all that is required is to hold the weight of the sand and soil that has been filled and compacted behind the wall facing. And for the second one is the vertical weight. And here, extra sand has been placed on top of the wall, and this actually introduces additional horizontal stresses onto the wall facing. And lastly is the lateral load, and here is the most critical part of the design, since additional loads have been hung from the pile in front of the wall, and this actually pulls the piles against the wall facing, causing the wall facing to be pushed out away from the actual wall itself. And then here are some of our goals for our overall project throughout the course of the past year. The first was not only to design the mechanically stabilized earth wall, but also to minimize the amount of the reinforcement strips. Because I had mentioned this is a part of a national competition, and the overall goal was to minimize the actual weight in the end. And then second was to not only implement the design from the theoretical 2-dimensional model and incorporated it into the 3D test box while satisfying the constraints of the test box itself. Our third goal was upon completing the testing, we were then able to have performance evaluations, and by monitoring how exactly the wall has failed in a certain instance, we were then able to better optimize the overall goal of our project. And lastly was to submit a design report. This was crucial since it was a determining factor of which teams got invited to attend and compete at the national competition. Now for a little bit of our schedule. On the screen is an overall summary of how our schedule panned out over the past year. We had highlighted a few of the 4 major milestones of our project. And what really isn't evident is the fact that as a group, we started our research over the past summer months. And this was necessary since the early due date of the project, which was the very beginning of January. We had to submit the design report to be considered for the national competition. For our project management, we show 2 tables here which are summaries of our budget. The first one shows the expenses of what exactly it costs to conduct the project, as well as attend and compete at the national competition, which actually took place a few weeks ago in Oakland, California. And then the other table is a summary of where our expenses actually came from, including our industrial sponsors.
All right, so the tasks carried out to complete our project were as follows. First, we had to look into the appropriate design method for our reinforcement strips. We chose the Federal Highway Administration Manual, or FHWA, for analyzing our self-weight and vertical loading conditions. However, the FHWA manual does not include or take into account for the pile loading condition. For this, we had to use the Fhwa method, which will be discussed in more detail later on in the presentation. After that, we implemented our design procedure into an Excel spreadsheet and used that to look into the correct layout for our strips on our wall facing. We then developed factors to calibrate this existing two-dimensional design method into the three-dimensional problem that we are facing. We also submitted our design report that qualified us to compete in the GeoWall competition at the GeoCongress in 2012, which was held in Oakland, California. We then completed a test box that was built to the specifications set forth by the competition, along with a load frame to help carry the load, the lateral loading condition. We then developed several compaction methods to maximize the density of the soil within the test box, and we successfully constructed the wall design in the laboratory, evaluated it, and was able to further calibrate our boundary condition factors and further modify our design to improve the unit weight of vapor reinforcement. Now, the image on the screen illustrates the traditional construction of an Msc wall. As you can see, the strength of an Msc wall is from the actual reinforcement that go into the soil layers. Now, an Msc wall can be more flexible and stronger and built higher than a traditional retaining wall. When comparing the concrete retaining wall to a Msc wall, after the Kobe earthquake in 1995 in Japan, the Msc wall still held while the concrete retaining wall was too rigid to hold up. Now, during our competition, several criteria were issued from the Congress. First of which was specifying the construction material. They specified the exact poster material to be used as the wall facing, the exact paper to be used for the strip reinforcements, and the exact tape that would be used to adhere the strips to the wall facing. They also specified several construction tolerances, which included the actual size of the construction box being 26 by 18 by 18, and the method in which tape was adhering a strip and facing at all times and being 2 by 2 inches large for the tape. They also specified the 3 loading conditions that Kalena spoke about, the self-weight, vertical, and the horizontal or lateral load, and the 3 major failure modes that they would be looking for, which would be sand leakage, in which 30 cubic centimeters, which is about the size of a standard medicine cup, would be leaking from the wall facing itself after construction. Deflection, in which the wall facing would deflect outside of the test box, and a wall collapse, which would be just the failure of the wall unable to hold the load. Now, if the team qualified for the competition, they were also met with time constraints. During the competition, we were allotted 15 minutes to construct the reinforcement strips. After that, we were allotted another 15 minutes to put those strips and adhere them to the wall facing itself. Once this stage was complete, we were given 20 minutes to construct the wall, which would be laying the strips and compacting the soil within the test box. Once the wall was completely constructed and wall facing was removed, the loading stages were also on time constraints, in which we were given 1 minute to apply the load, and the wall would then have to hold that for an additional minute. Our final design would have to be based on, our final product would have to be based on design rather than a trial and error method. I'll turn it over to Jim.
Thank you, Kyle. I would like to walk you through the 3 loading conditions and how those stresses affect our wall facing. The first loading condition is the soil's self-weight. We analyzed this using the Rankine method and the equation above. This produced a theoretical stress distribution, which we compared to our stress pad testing depicted as our measured stress distribution. The second loading condition is the 50-pound vertical weighting. This was analyzed as a point load on our soil and calculated for using the equation above. Well, you can see our theoretical stress distribution as well as our measure. The third and final loading condition is the 25-pound lateral surcharge applied to the piles. This produces a horizontal force acting on the front face of our wall. And we analyzed it using the Py curve solution shown above. This relates load to the deflection of the piles. And as before, you can see our theoretical stress distribution as well as our measure. So now that I showed you the 3 loading conditions and how those stresses affect our wall, I will discuss how we design the reinforcement to withstand those applied loads. We identified two critical failure modes, pull-out and breakage. It should be noted that pull-out is the lack of friction between the sand and the reinforcement that causes it to pull out from the granular backfill material, and breakage is an excess or overload of stress on the strip area that causes a rip, most commonly at the attach points. Both failure modes will result in a catastrophic failure. The FHWA method was implemented in calculating the factors of safety for both pull-out and breakage in the reinforcement, and we integrated that into our Excel program. So we effectively designed our wall, but now we need to verify how well it would perform to calculate the stresses. We did this by loading the wall design to failure every time, regardless of whether it held the 3 loading conditions successfully or not. We recorded high-speed wall failure videos to document how and perhaps figure out why our wall was failing. Both of these helped us calibrate our boundary condition factors, which would go into our Excel sheet. And in addition, we conducted the stress pad test, which I showed earlier, to identify the stresses on the wall facing. All of these helped us evaluate and maximize the performance of our mechanically stabilized earth wall. Ashley will now discuss the final design.
So after this iterative process of design, construction, and evaluation of our wall, we came up with the final design, which is depicted in the top right corner of the screen. The actual geometries of these reinforcements are shown in the bottom left. The factors of safety that we calculated using the design methods and the stresses that were discussed earlier in the presentation are shown in the top left corner of the screen. And as you can see, there's no factor of safety calculated for the strip row number 1, because that strip was implemented during our design phase to combat some deflection that we were having with our wall. The material properties that we used in our design are shown on the bottom right corner of the screen. We took this final design to the national competition with a final reinforcement of 5.89 grams. And we'll now show a brief clip of the competition that shows, maybe it'll show. Basically what you're going to see here is us adding sand to the box and laying our reinforcement strips in layers, and then compacting the soil over the layers so that we can maximize the amount of friction on the reinforcement strips to prevent pull-out failure. And after that, in the video, you can go to the next slide with the pictures. What you're going to see is that we started to load our wall for the 3 different loading conditions. We took off the front face, and we allowed the wall to sit for 1 minute with its own self-weight, which is over 500 pounds of sand behind the wall facing. And then they checked it. We then added the 50-pound vertical surcharge load and then the 25-pound lateral load, which we held approximately 20 out of the 25 pounds before our wall failed catastrophically. And of particular interest on this slide is the wall facing after the failure, which is depicted in the bottom right corner of the screen. It shows that the 3rd row of strips is completely absent from our wall facing. This is due to the fact that during the competition, our strips failed in shear at the connection points. We think this might be due to the fact that the humidity is different in California than it is here, which may have changed the properties of both our wall facing and our reinforcement strips, as well as differences in the sand that we use at the competition, the sand that we were testing in the lab. So in conclusion, our group took a 2D plane string design method and applied it to a complex 3-dimensional problem. We successfully constructed this design in our lab several times before taking it to the national competition, where we represented Widener as the only team consisting of solely undergraduate students. And though our wall failed catastrophically, we did learn a lot from this and have a lot of recommendations for future groups to continue the research on this topic. Some of the continuations we'd like to suggest are more research into the connections, the actual stresses made by different connections at the wall facing, as well as more research into different compaction methods that we could use to help reduce those stresses in those areas. and also a procurement of small samples of different sands within the given grain size distribution to help us to sort of make a design that would cover all of the different types of sands that we could encounter at the competition. We would also like to have them explore alternative strip geometries, since the winning team at competition this year had an interesting strip geometry, and we'd like to look more into that. And we hope to take all this information and pass it down to the team for next year so that they can go to the national competition and take home the Edinburgh Cup. Does anyone have any questions? I'd like to thank you for your time and attention.
So do we have any questions for this group? Yes, sir.
Two questions. One, what is the material of your strip until here? And the other is, it's a complicated problem. And you will be surprised to see, because you say design and not trial and error, if you somehow, somebody has to try some finite element analysis. Because you have so many stresses there, and you have a different kind of sense, as you say. So have you given any thought about what strip do you use?
The strips reinforcements had to be 20-pound craft paper.
Okay.
And as far as the software analysis, finite element analysis, we tried software analysis, but they weren't able to take in the fact that our strip strength was only 29 pounds per square inch. It's very, very small. We looked into finite element analysis. I know Kalena was starting it, but there just wasn't enough time for us to completely implement that.
You have to try, somebody has to try sometime. It's really going to give you a different dimension.
We'll go over here first.
So the moisture content of the actual material that was put in your bag, in your box, was not part of the criteria of the competition?
No. Basically, it was a roll of craft paper that you could buy at any store, but it was specified of what type of craft paper it was. And we think that, here the humidity is a lot different than it is on the West Coast, and we think that that played a role in weakening the strength of our strips and the way that they were able to deform with the load.
Right in the middle.
You talked about the failure of two types of construction in Japan. What kind of reinforcement was in the walls that failed? Was it fencing, wire fencing, or what kind of? What I'm used to is some wire fencing that is used to reinforce the concrete.
The walls that failed in Japan was a cantilever reinforced concrete wall, typical for retaining walls, while the Msc walls used were a geotextile membrane that they used for their reinforcements.
So it was a textile that held.
Yes, they held.
And what failed?
The regular retaining wall based nothing more than reinforced concrete.
Yeah, well, what was it reinforced with? You may not even know, but I'm just real
I assume
curious.
standard rebar.
Standard rebar.
Okay, we have time for one more question. Ready?
How did you compact the sand, and how does that relate to typical construction methods for a real wall?
You want to go back to the slide with the competition photos? I think there might be one on there. We actually poured the sand into the box, laid the strips, and then poured more sand a little bit over them to give them a little bit of a buffer. And then I actually, there's a picture of it, the top right corner. I stood inside the box and held the wall facing against the box so that we wouldn't get sand leakage. And the rest of the group members actually used rubber mallets on the side of the box to cause vibrations to compact the sand.
And we actually had a piece of plywood that was cut to fit inside the box that she was standing on.
So it was pressure throughout the whole box to create that.
Thank you very much.